The paper titled, Molecular Design Principles of Helical Pyramidal Chirality Self-Organized from Achiral Hexakis, alkyloxy, triphenylene, explores the structural analysis of self-organized 3D helical and non-helical pyramidal and discotic columns formed by hexakis, alkyloxy, triphenylene, HATN, molecules. The authors begin by introducing HATN, a classic group of discotic molecules that self-organize into columnar liquid crystals. Despite being invented 45 years ago, the structure of the crystalline assemblies of HATN molecules has been neglected until now. The authors first discuss their recent discovery that the crystal state of HAT4 consists of a highly ordered 8/1 helical chiral pyramidal 3D self-organization. Building on this finding, they investigate the structural analysis of all 3D self-organizations of HATN molecules with N equals 4 to 12 carbons in their alkyl groups. Surprisingly, they find that the highly ordered 8/1 helical chiral pyramidal crystalline columns assembled from the crown conformation of HAT4 are also encountered in the crystalline periodic array of HAT5. HAT6 self-organizes a 5/1 helical chiral pyramidal 3D column, while HAT7 to HAT10 maintain their crown conformation in their 3D supramolecular pyramidal columns but exhibit a non-helical criss-cross arrangement. HAT11 and HAT12 self-organize 3D non-helical columns from criss-cross arrangements of disk-like conformers. To determine the structures of these 3D helical and non-helical pyramidal as well as non-helical discotic columns, the authors use oriented fiber X-ray diffractograms reconstructed with the help of molecular models. They find that a single self-assembling building block, HATN, can self-organize either helical chiral pyramidal or non-helical pyramidal or even non-helical discotic assemblies via two of its constitutional isomers. The authors highlight the implications of their findings on the understanding of helical self-organizations, raising questions about the exploration of helical self-organizations derived from long alkyl groups when short alkyls seem to be more ideal for the self-organization process. They propose a hypothetical explanation for their findings and discuss the impact on the field of helical self-organizations. Overall, this paper presents a comprehensive introduction to the study of helical pyramidal chirality self-organized from Achiral Hexakis, alkyloxy, triphenylene. It provides a clear overview of the research background, the aims of the study, and the main findings, setting the stage for the subsequent sections of the paper. This figure shows the structures of hexakis, alkyloxy, triphenylenes HAT-N with N equals 4 to 12. These compounds serve as the building blocks for the self-organizing assemblies studied in this research. The structures consist of a central triphenylene core with multiple alkyloxy chains attached to it. The length of the alkyloxy chains varies depending on the value of N, which ranges from 4 to 12. The figure also includes a simplified representation of the fiber diffraction pattern for the helical self-organized assemblies. The significance of this figure is that it provides an overview of the molecular structures of the building blocks used in the study. These structures play a crucial role in determining the self-organizing behavior and properties of the assemblies formed. By varying the length of the alkyloxy chains, different assembly structures can be achieved. This information sets the stage for understanding the self-organization processes described in the subsequent figures. This figure illustrates the 5/1 helical assembly of hexakis, alkyloxy, triphenylene, HAT5, and presents its structural parameters. The helical assembly is characterized by a unique arrangement of the building blocks, forming a helical column. The figure includes a representation of the fiber diffraction pattern, which corresponds to the St. Andrew's cross pattern observed in the helical diffractograms. The significance of this figure is that it demonstrates the successful formation of a helical assembly using HAT5 building blocks. The structural parameters provide insights into the arrangement and packing of the building blocks within the helical column. The fiber diffraction pattern confirms the helical nature of the assembly and provides experimental evidence for the specific arrangement of molecules within the column. This figure presents the simplified representation of the fiber diffraction patterns of the helical assemblies formed by hexakis, alkyloxy, triphenylenes HAT-N with N equals 4 to 12. The diffraction patterns exhibit characteristic St. Andrew's cross patterns, indicating the presence of helical columns in the assemblies. The significance of this figure is that it demonstrates the generality of the helical self-organization process using hat-end building blocks with varying chain lengths. The presence of the St. Andrews cross pattern in all the diffraction patterns confirms the helical nature of the assemblies formed by these building blocks. This consistency in the diffraction pattern suggests the existence of a common self-organization mechanism that is independent of the chain length. This figure shows the structures and simplified representations of the fiber diffraction patterns of the non-helical pyramidal columns assembled from Hexakis, alkyloxy, triphenylene, HAT6, and Hexakis, alkyloxy, cyclotriveritrylene, HATCTV6. The non-helical pyramidal assemblies are characterized by a different arrangement of the building blocks compared to the helical assemblies. The fiber diffraction patterns exhibit a different pattern, distinct from the St. Andrews cross pattern observed in the helical assemblies. The significance of this figure is that it highlights the ability of the building blocks to form non-helical pyramidal assemblies, in addition to the helical ones. The structures and diffraction patterns provide evidence for the different packing arrangements and spatial organization of the building blocks in the non-helical assemblies. This finding expands our understanding of the self-organizing behavior of the building blocks and the potential for diverse assembly structures. This figure presents the structures and simplified representations of the fiber diffraction patterns of the non-helical discotic columns assembled from Hexakis, alkyloxy, triphenylene, HAT4, and Hexakis, alkyloxy, cyclotriveritrylene, HATCTV4. The non-helical discotic assemblies exhibit a different arrangement of the building blocks compared to the helical and pyramidal assemblies. The fiber diffraction patterns show a distinct pattern, different from both the St. Andrews cross pattern and the non-helical pyramidal pattern. The significance of this figure is that it reveals the capability of the building blocks to form non-helical discotic assemblies, further expanding the range of self-organizing structures that can be achieved. The structures and diffraction patterns provide insights into the packing and organization of the building blocks in the non-helical discotic assemblies. This finding highlights the versatility and flexibility of the building blocks in forming diverse assembly architectures. This scientific paper discusses the molecular structure and self-assembly behavior of a series of compounds called HAT-N, where N ranges from 4 to 12. The authors investigate the different thermotropic phases exhibited by these compounds and analyze their thermodynamic parameters, such as enthalpy and entropy changes. They also examine the structures of the self-assembled columns formed by the HAT-N compounds using X-ray diffraction techniques. The results reveal that the columnar supramolecular structure of the HAT-N compounds depends on the length of the alkyl chains and the number of aromatic rings in the molecule. At lower values of N, 4 to 6, the columns exhibit a helical structure, while at higher values of N, 7 to 10, the columns become non-helical and pyramidal in shape. At N equals 11 and 12, the columns form non-helical discotic structures. The authors also discuss the implications of these findings for the design of self-assembled structures and the potential applications in various fields. If you are an author or copyright holder for the work presented in this video and you have any issue with the existence or contents of this video, please let me know.